Everybody. So my name is Chunyi Zhi. I work in Department of Material Science and Engineering in City University of Hong Kong. So my research is about flexible electronics. This is the first time I participate in the conference of IEEE. I work on battery, I work on chemistry, but my battery can be a great power solution for flexible electronics. In the next 30 minutes, I'm going to introduce you my batteries. The concept of flexible battery is quite simple. Typically, we have these types of battery, which is rigid. You have rigid structure, right? So you have electrode, electrolyte, and together with the package materials. And we're trying to make it to be flexible like this. This is a prototype by Samsung company. They're also working on flexible batteries. So why do we need a flexible battery? This is because recent years that, for example, in your field, you may have a lot of flexible devices, wearable devices. You have flexible sensors, flexible circuits, and a flexible display. But battery, without a battery, your system cannot be fully flexible. It must be pseudo flexible. So if you want a fully flexible system, flexible batteries cannot be avoided. It is sort of difficult because battery is an electrochemical device. If we have smart clothes, that we may have different sensors integrated on these clothes, and we have data analysis, wireless transmission, together with a power solution, flexible power solution to all these systems. So this may be in the future. Okay, we have different types of flexible batteries. But if you look into the requirements of different flexible electronics, different wearable electronics, that they have different requirements on flexible batteries. For example, on this side, typically they are collecting some signal. So our battery need to power some sensors. And this side, you may have more functions. You may have a lot of functions. You may need to heat up, for example, here. That in that case, that you need a lot of power. If you analyze the wearable electronics here, they use lithium battery, but some of them, they may only need a very small size lithium battery. You don't need a lithium battery. And eye mask, that they use zinc primary battery. So they have different requirements on, for example, flexibility. For example, this one's only moderate for a watch as a watch band. It's only moderate. But for others, for example, okay, it's not listed here. For example, here, it must be very soft. Should be very soft, and its contact with your skin, it should be extremely safe. But on the other hand, that you only need to power one or two sensors. You don't need a very high energy density. So have different requirements on different purposes. So we figured out that for flexible batteries, it can be lithium battery, it can be other batteries for different purposes. For example, for the very soft, very extremely safe battery, we choose a zinc manganese oxide battery. So this one is based on zinc, and we use water as electrolyte. So this whole system is very, very safe, and it can be rechargeable. This kind of technology is old, but this kind of battery you can buy from market. It's primary battery. It cannot recharge. It cannot be recharged. So in recent years, we developed different technology to make this battery be rechargeable. So this is one of our example to develop zinc-ion battery based on aqueous electrolytes and make it to be flexible and very tough. And we also demonstrate our batteries can power a lot of flexible electronics. So this is how we fabricate the electrolyte. So since I'm talking in the IEEE conference, I don't go to details of the chemistry. Generally, we just put some chemicals here. We stir, then we inject the gel into a kind of separator. We got a piece of, we call it HPE. which is a separator together with the electrolyte. It's quite tough. And this is a piece of so-called HPE. If you freeze dry, you got a lot of pores, and the pores can hold some water in the pores. Then the water can conduct ions. That's why we use this as electrolyte. If you sandwich this with two pieces of electrode, you can get a very thin battery, which is quite soft, quite flexible. The thickness can be very thin. If you check the electrochemical performance, you got Chunyi curves, very good shape of the curve, and very good performance if you compare with other type of flexible batteries. And also, you can cycle charge cycles for 1,000 times, so it's quite good battery, extremely safe. I'm going to use this video to demo safety and durability of this battery. You can even put it on fire. You don't have to worry it can spoil. It cannot spoil. You can wash it. You can wash it. You can drill it. You can also even sew on the clothes, like a piece of clothes, a piece of fabric. Cut it into different pieces, can still work. Okay, of course, when you do all of this, you're trying to touch this device that you lose some capacity, a little bit lose the capacity, but even 800 times bending, you only lose around 7% of the capacity. It's not a big deal, let's say. If you do it, put it on fire for 5 minutes, you lose a lot of capacity, but this is only because that water evaporation. If you put a drop of water on top, that you can partially recover the capacity. And the device, the battery device, can power some flexible electronics. This is our let's say our demonstration. We use it to power a pulse sensor with 4 pieces of battery, because this one needs 6 watts and we have only 1.5 watts. This is your 3 pieces of battery to power a smartwatch. We can eventually make it. This is a smart insole powered by 2 pieces of our batteries. Step on it, and you can run. You can jump. You can hope you can run. You don't have to worry about this malfunction of the battery. This guy is run 2 kilometers and also work 15,000 steps, so the battery can support his work. So one of the problem of this battery is based on aqueous electrolyte. It's based on water. So water can be frozen at low temperature. So we're trying to solve this problem to fabricate a flexible battery with water, with hydrogel, but it can sustain at sub-zero temperatures. This is how we design the hydrogel electrolytes. So this hydrogel electrolytes, even at minus 20 degrees C, and 10 degrees C is good. This is a normal electrolyte, normal hydrogel. At minus 20 degrees C, our hydrogel can still be tested, but this one has been is frozen. And if you bend, we can still bend. You can still compress at minus degrees C. You can still have this kind of flexibility, and it is still conductive to ions. This is conductivity to ions. So this one, like, it's quite safe. You can freeze it in a piece of ice. It can still work. You can trace it. You can also hum it. It's still very safe. And this is a normal battery that at sub-zero temperature degrees C, that you can, if you bend, you got some broken here, but our one can be very intact. And this is a performance. This is a normal battery with aqueous electrolytes that at minus 10 degrees C, the voltage, the capacity will drop. You don't have any capacity anymore. And for our batteries, we have some fluctuation in terms of the capacity, but not that much. We still have a certain amount of electricity in our batteries. Okay, so this is another demonstration. The other one is we also trying to avoid water. Although it's a aqueous electrolyte battery, we can also try to fabricate a kind of so-called solid-state zinc-ion batteries. The solid-state one is based on a piece of polymer electrolytes. instead of water. There's no water in. The reason is that although we can achieve very good performance with the battery, but if zinc is negative in terms of if you put it in water, that you got hydrogen evolution, hydrogen bubbles will come out. It's like this. If you put a piece of zinc, this is zinc coated on copper, that you can have some bubbles out. Also, if you do charge discharge, you can have some kind of dendrites growing on the surface of zinc. So we'll eventually rule the problem of dendrites got a short circuit here. The short circuit here. This is zinc symmetry batteries. You have two pieces of zinc to cycling that you see the surface is growing some dirty stuff. Then the dendrites will penetrate your separator, reach it to another side of the electrode, then got short circuit. We're trying to solve this problem. For example, we use graphdiyne coating on the surface of zinc, that you got some ion channels. The ions can go through the channels to unify the zinc deposition. You can get a very good stability of the cycling. So this is one of approach, but the ultimate approach is use solid state device or change the aqueous electrolyte to be some others. For example, here we use ionic liquid. We use ionic liquid. This one is demonstrate ionic liquid has wide water. If you compare with water, the green one, and also the green one and the blue one, that you see that the voltage window of ionic liquid is much higher, much wider than water. And also, if you look at here in water, if you put a piece of zinc in the water, that you got hydrogen evolution, that the hydrogen amount will accumulate, keep increase. But if you put it in ionic liquid, it can be very stable. There's no hydrogen evolution, no hydrogen be produced. And if you put this zinc anode in the electrolyte, in the ionic electrolyte, you got a very small surface. Instead, if you put it in water, you got a very rough surface, because the zinc ions, the deposition behavior of zinc ions in different electrolytes are totally different. The ionic liquid can be much more stable than others. So with this, we pair our zinc with a PBA. This is PBA, this is zinc. This is a piece of polymer electrolyte. Together with the, we use the ionic liquid. That ionic liquid we developed as a kind of plasticizer. So we pair this, we got a very beautiful discharge curve at pretty high voltage. And it can be very stable. For example, sometimes cycling, you can still have almost 100% or 90% of the capacity. And it will make a large size batteries. There's no swirling problem. There's no gas coming out. So this is quite stable battery. And if we use this solid state electrolyte, we can fabricate also a flexible device. You can even cut it. But we also cut the battery equipped with hydrogel electrolyte. But in that case, if you cut, the hydrogel is exposed, the water will be evaporated. Then after a certain time, that you will lose the capacity, you will lose the battery will be broken. But with our polymer electrolyte and very stable ionic electrolytes, you see, if we cut, we don't need to seal it. We just keep it exposed for a pretty long time, for let's say 5 days. The capacity will still keep around 100 or 100% of the capacity in terms of the capacity. This is capacity. And if you cut different times, you still have the capacity well kept. And also because it's ionic liquid, so it's not very sensitive to temperature. You make it at low temperature, high temperature, you can still work up to 7 degrees C, lower to minus 20 degrees C, that you can see the very stable performance. And it can totally recover even at minus 10 degrees C, that you have lower capacity, but it can fully recover if you're back to the room temperature. Okay, so this is about our work on flexible zinc ion batteries. We also work on flexible lithium ion batteries. For example, this one, the flexible lithium battery we developed can have different flexibility, and also we equip it in a smartwatch like this, like wristband of smartwatch. It provides additional 380 milliampere hour to the smartwatch. It can sustain the whole device. It can sustain more than half a month, or even 20 days. But lithium battery, we have a lot of constraints in terms of the materials, because, for example, you have to use plastic aluminum plastic film to seal the lithium batteries. Otherwise, if the electrolyte of lithium battery is exposed to water, exposed to air, then the battery will be broken. So we can only achieve the flexibility by this one, the structural design. We did some finite element simulation to try to optimize the battery's structure. So we design different structures. We use the current collector, aluminum film, and copper film as a standard, as a criteria to study the different deformations of the battery, that the stability. For example, here, this is stress. The yield strength of aluminum, of copper, around 200. On different deformations, you see we got some color of red here around this number, but it's still not reached to the yield strength. So generally, the battery can still survive on very severe deformations. And we also adopting this concept, that we also consider, for example, our fingers. We have some joints here, and for each piece of the finger, that it has no flexibility, but the whole finger can be very flexible. This is because of joints, right? We design some joints for our batteries, and also, especially with simulate, we mimic the comfort structure of the bones here. This is very important, actually. The very small design solve a lot of problems, that you can achieve very large bending or some even twisting behavior with this kind of design. So also for the ion storage unit, it can be cubic, it can be cylindrical, it can be triangular, different shapes, achieving different flexibility. For example, for the cubic one that we can have, this is a cubic unit. You can see here, 1, 2, 3, 5, and connect with the softer pieces. And on different deformations, it can be flexed, can make it to be a ring, fold, and twist. And this is cycling stability. It can be very, very stable. In terms of capacity, there's no fluctuation. And this charge-discharge curve is totally overlapped. You don't see any performance degradation on the different deformations. And if we only ban it, even for 200,000 times banning, that you don't see very remarkable capacity degradations. You can still keep the original capacity. The twisting. Okay, twisting, dynamic twisting is like you bend the battery like this. You bend the battery like this. We did it 25,000 times. And okay, it's quite stable. We got slight degradation of the performance, but generally it's no much difference in terms of capacity. And if you see, this is a dynamic twisting, that see the voltage discharge. This is zoom in voltage discharge. The voltage there's no fluctuation of the voltage. That means if you do the twisting for a battery, and you still have very stable voltage output. You don't see any fluctuation. That's quite important to when you power a flexible device. Also, we can make it to be stretchable. For example, if we use cylindrical types of and storage units, it can be from normal, make it longer, and you can also fold it even or wing it. Or you have some complex deformations, bending together with twisting, whatever. This steel can be very stable, very well overlapped charge curves. And this is dynamic strengthening, keep strengthening for, and then we do cycling stability test. Meanwhile, the cycle number is 14 times, but the strengthening has been 100,000 times. It's quite stable. We got some degradation, but not that much. And we use this battery to demonstrate a lot of applications. For example, this is an earphone that we put our battery here. Typical earphone, we put a battery here, but it's not well balanced because on one of the earphone, yeah, you got a battery, but this side you don't have battery. But we put our battery on the top. It's well balanced with distribution, and we can be an astral battery for even longer time, lifetime of the earphone. And this is a smart watch. We make a smart watch to work on 22 days. And this is another customer devices, and also this is to charge a mobile phone. I can have some video to demonstrate some application, safety of our flexible. Oh, sorry, this is a kind of application demonstration. This is for smartwatch. This is wireless charging band. Then if you put the watch on, it can be wireless charge. And on the other devices, for example, this is a kind of portable anion producer that can clear, for example, smoke. We make it to be a kind of fashion designed decorator to women. And also this can be a kind of GPS used for pet. Our battery is inside and power this GPS module is used for dog, cat. Oh, this is our flexible batteries. And also this is earphone. You can do any bending to it. Yeah, it can be used for pretty long time. It can be an extra battery, or it can be a well-balanced weight distribution of the battery. This is luminescence. It's light emission devices. Okay, this is luminance code. Okay, so this is our demonstration. I'm gonna sum up. Our flexible batteries it can be a power solution for flexible electronics. We have demonstrated some applications, and also our batteries is very safe, much safer than rigid structure batteries because we consider this battery is attached on the skin, on the body, so it has to be safe. But we need more optimization in terms of both the energy performance and mechanical reliability, even together with, for example, comfortability. And we are I wish to, for example, collaborate with you to look for more applications for the batteries, for our flexible batteries. Okay, I would like to acknowledge a few colleagues working together with us from, for example, Professor Hu from Hong Kong Polytechnic University from Department of Textile, and all group members and funding sources. I would like also to thank you for your attention. Thank you.